And we're going to start off this session with talking about FPGAs. I don't know if you all lead the group to talk about it, but FPGAs are really a very important part of technology. They're taking over almost everything today. And our first group consists of Dylan Peck, Jeff Blanda, and Sweta Raju. And I'm not sure who's going to be the lead on that.
Dylan will be presenting.
Okay, and Dylan, I've been suggesting the groups. I should have done it before you put up your first slides. You're all ready.
All right, yeah, so we're the Video FX FPGA group. Yeah, so I'm Jeffrey Blanda. I'm the team lead. I'm a senior computer engineering major. I actually have a job lined up post-graduation as a logic design engineer. Shweta was unable to come today, but she's also a senior computer engineering major involved with semiconductor simulation research and the president of TCNJ's SWE and Academics Affairs Chair for the TCNJ chapter of Theta Tau. She's in pursuit of a full-time software engineering role post-graduation.
I'm Dylan Peck. I'm a senior electrical engineering major here, and I am part of the engineering fraternity Theta Tau, as well as treasurer of the Electrical and Computer Honor Society, HKN here, as well as the captain of the track and field team here at the college. And I'm also part of the Engineering Honor Society, Tau Beta Pi. And I'm looking for a full-time power engineering role position post-graduation. So our goals for this semester were to drive a color VGA display at 800 by 600 resolution using an FPGA. We will include a hardware accelerator to render triangles, which is used for generating 3D graphics. We are going to include an interface to allow a host to send graphics commands to the FPGA, which in our case for our project is a Raspberry Pi. We are going to render pixels at the maximum possible rate, and we are going to create or obtain a 3D model expressed as a list of 2D triangles with 3 vertices and pixel values and projected down from 3D models and use these to demonstrate drawing speeds. So our components for our project consists of a Xilinx XC7A100 FPGA, as well as the Raspberry Pi 2B.
So this is the top level architecture of our design. So if you look on the right side, we have the FPGA, which contains an interface to communicate with our host computer, a FIFO buffer, which holds all of the instructions sent, a command processor that'll actually route those instructions to the module associated with them based off their opcode. We also have the line drawing module there. We did implement a triangle drawing module since that hasn't been updated on this chart. And then we have a write multiplexer, a frame buffer, and a display engine, which all kind of work hand in hand to draw the image in the frame buffer to the VGA display. Then on the left side, we have the Raspberry Pi, which houses a demo application, which runs off of Linux and uses the GPIO to communicate with the FPGA.
So this is our project timeline. So as of last semester, we successfully created a part of our demo presentation last semester where we were able to draw lines on a screen from the Raspberry Pi to communicate to the FPGA and then output on the VGA display. So for our demo application, which we will get in later, we were able to draw lines on screen connecting dots to form the Utah teapot. So this semester, we are focusing on designing and implementing our 3D to 2D transformation, and as well as designing and implementing our triangle drawing, which we have just finished. So now we are just finishing up our 3D to 2D transformation and our demo application for the end of this semester, as well as optimizing and measuring interface throughput and verification and debugs.
So about VGA, it's an older video standard released in 1987. It's specifically designed to navigate the electron beam inside a CRT display. So utilizing 2 sync signals, you're able to control the beam vertically and horizontally. Since its release, it has been modified for higher resolutions, including Super VGA, which is what we use to achieve the 800 by 600 resolution that we set out for in this project, as opposed to, I believe, 640 by 480 was done previously in a similar project, but we wanted to add that extra level of detail and complexity. So this is how we're outputting the VGA signals. So we have at the bottom the horizontal sync and vertical sync pins, which drive the display. But we also have red, blue, and green signals here through a ladder of resistors, which essentially acts as a digital to analog converter. So currently, we're only using 8 bits of color since we have a memory limitation with the FPGA board we're using. So we do have a lookup table to actually map those 3 bits and 2 bits based on which color it is to the 4 bits that you see here so that we can get the full intensity of red, full intensity of blue, and everything in between as much as possible within that resolution. So this is actually the output from our monitor when we connect it to the VGA or to the FPGA. We're able to create these horizontal and vertical signals using a counter, basically. And so the monitor will detect that that is in fact 800 by 600 resolution, and it'll output the frequency of the signals. So the next task was the frame buffer. Now that's actually just a memory space that stores the pixel information for each pixel on the display. Modern technologies use 2 frame buffers as they write to one while reading from a second one. That way they can try to prevent some of the issues, like if you're drawing an object and you're outputting to the monitor, you don't want that object to only show up halfway. Unfortunately, since we're limited by memory, we're unable to do that. So we're only using 1 frame buffer, which does introduce this issue a little bit, as you'll see later on. So this is the output of our frame buffer. We were actually able to preload the memory with specific values that gave us this test pattern when hooked up to our monitor. So this is just showing that the frame buffer worked as intended. So our next task was one of the more complicated ones. So this is the Bresingham line drawing algorithm. It's essentially an algorithm that can draw a line from point A to point B, outputting each individual pixel that it has to traverse to get to the second point along that line. Now, this is specifically designed to be heavily parallelized, so there's no multiplication or division involved, and we were able to get approximately 1 pixel per clock cycle, which is, for this project, as good as we can get. So this is our demo application using that line drawing algorithm. We were able to actually map 2D points of a teapot and draw each of the lines that you see there.
So for this project, we used a host interface to communicate from a host machine, and in our case, it's the Raspberry Pi, that can send data back and forth between the host and the subsystem. For our project, we will not have to send any data from the FPGA back to the Raspberry Pi, so it's a little bit easier to just have us just send one way from the Raspberry Pi to the FPGA. And to be able to send over instructions from the Raspberry Pi to the FPGA, we had to declare and connect the correct GPIO pins for our model of the Raspberry Pi, and then declare and connect them to the corresponding PMOD pins on the FPGA using a ribbon cable. And as you can see in the diagrams here, these are the corresponding GPIO pins for the Raspberry Pi that's on the Raspberry Pi, and we had to go through and declare each one that we wanted to use. And then on the left, you can see is our code here of us declaring all the pins and also declaring our RTS and RTR, which is ready to send and ready to receive, so that when the Pi is ready to send over data to the FPGA, the FPGA can acknowledge that, and it'll be ready to receive. So then we can send data over and then go back and complete the cycle. And in order for us to be able to draw lines, the FPGA needs a certain instruction from the Pi as to where and what color to draw, as well as the X and Y coordinates. So below shows the 72 bits that are included in each instruction to be able to draw a line. And the format of the instruction is based on the communication itself between the host computer in general and the FPGA, and not on the Raspberry Pi itself. So the first 3 bits are our opcode, then followed by the color code, our 0.1 for X value, Y1 value, and then X2, Y2, X3, Y3, etc.
So now that we're able to draw lines between 2 points, the next step in our project was to be able to draw triangles. Now, obviously, we could draw a triangle just by drawing 3 lines, but we wanted to fill them as well via triangle rasterization. So we wanted to keep with the heavily parallelized theme. So we implemented 2 Bressingham line drawing algorithms to basically draw 2 of the triangular lines and then fill in between them. So if you can move on to the next slide. So this is the output example where we created a triangle, and essentially the left side and right side each were drawn progressively, and then the middle section is filled in as each algorithm progresses. And if we have a case where one is moving too fast, it'll actually slow down and wait for the other one.
And our next step is to finish and complete our 3D to 2D transformation. So just a little background. So 3D to 2D transformation is used widely in the computer graphics field. It allows for 3D animate objects to be transformed into 2D inanimate objects. And our goal for this semester, as I said, is to develop a program that can take a 3D matrix of coordinates, convert it to 2D points, and send over to the FPGA to be drawn, as well as incorporating an angle and scale, so we can scale triangles in that factor. We are currently about 75% done with this. We are just finishing up the last bit and trying to debugging a little bit, as our code's just not working properly right now. Just to conclude, we're going to design and implement a simple FPGA-based 3D graphic accelerator, and a demo application will be created using a Raspberry Pi as a host computer. Any questions?
What do you see in terms of limitations with FPGAs going, what you can do with a larger FPGA, for instance? How does the availability of FPGAs affect future work?
Well, what we're seeing with this project is that you don't actually need that much power in the FPGA itself. So with how FPGAs have been evolving and progressing, this is a good thing that you could add on top of existing projects. You know, why not add an interface that you could actually see? The only issue is that it's very memory dependent. That's why we're stuck at 800 by 600 with 8-bit color. We could up that to 12-bit color, but then we'd have to reduce our resolution, or we could increase the resolution and reduce our color depth. So that's really just the limiting factor.
Okay. I know there's a great deal of development in the FPGA world.
Any other questions?